Okay, so let's begin with a scientist, and his name's not written down here, but you guys ever heard the name Anton Lavoisier? I'll write it out for you. Not that it probably is going to be on any tests, but Anton Lavoisier, he discovered something really critical back in like 1610 or sometime way back then. I don't know the date off the top of my head. He discovered the law of conservation of mass. And I want to take you back to a time in chemical history where scientists didn't fully know what they were talking about because they didn't understand internal structure. They didn't know about protons and neutrons and electrons. They didn't even know about nucleus yet, right? They basically just thought that all matter was like billiard ball model. You guys ever heard of that one before? Where like carbons are carbons, nitrogens are nitrogens, that you can't break them in half. And they didn't fully get it at the point. Okay, so I want to present a scenario to you. You are burning some wood in your fireplace, and you start with this log of wood, and it's 20 grams, 20 kilograms. Grams is too little. 20 kilograms, and you burn it. And after it's undergone a chemical reaction, clearly we know it went through a chemical reaction because energy was given off. Um, we saw new states of matter develop. There's a new color, like the ash that's left over, right? So it starts with 20 kilograms. It goes a chemical reaction, and then you weigh all the ashes when you're done. And when you're done, the ashes only weigh 10 kilograms. Well, this doesn't really make a lot of sense now that we know about the law of conservation of mass. But at the time, that made sense to everybody. Because you know what they thought is that the missing mass was the energy. They thought that, oh, the reason why it went from 20 kilograms down to 10 kilograms is that mass was given off as energy. Now, for those of you guys who have learned physics, E equals mc squared, there is a relationship, but that's not what happened. Where'd the missing mass go? What happens when you burn stuff? What's one of the byproducts? Yeah, smoke. What kind of gas? CO2, yeah, carbon dioxide gas, right? And so, yeah, you might have some carbon left over. You might have, but like one of the byproducts is carbon dioxide gas that would be released. And Lavoisier realized that he had to capture all of the products and all of the reactants to be able to measure them. And he discovered that mass is neither created or destroyed. He realized that the amount of like reactants that you have has to equal the amount of products that you have, and it needs to be all of your products, right? Like if you have a product that was a gas, they might have forgotten to count that, right? But if they did weigh the gas, then it would account for that. Lavoisier was actually doing an experiment with something called magnesium, and you've probably seen me burn magnesium before, or maybe Lav burn it before. It burns like super super bright. If not, I'll do it another day. And he was watching an experiment where magnesium was getting burned and it was turning into magnesium oxide. And he was actually witnessing the opposite effect. So you know how I just described to you like burning a log makes it seem like you're missing mass? He actually was trying to solve this problem here where when you start with magnesium, let's say you start with 20 grams, he burned it and he ended up with 32 grams. And this really seemed to break that law then, because at least it made sense that the missing lost mass was the flame, the fire. You know what I'm saying here? But here, magnesium was burning, producing a flame, and yet it was adding more mass. What were they missing in this example? What's the other thing that I should write out? Yeah, because really magnesium, just like anything that burns, needs the presence of oxygen to burn. You guys know this about combustion? Three things you need. You need oxygen gas, you need a fuel, you need a flame to get it going, right? The three components. And so what he realized in the counter example is that there must have been 12 grams of oxygen that was being added to the magnesium to then make the magnesium oxide so that somehow there was more mass being created. And it sounds so simple to us now because I'm sure most of you guys would probably think, well, how this is obvious, but you got to think like this is before microscopes. This is back when they still thought that maybe fire was an element. You get what I'm saying here? And so if I can go back up to my slide here, this was such a huge important concept, the idea that we can't add or create stuff. And what it really led to then, oh, here's the example I had. Sorry, to my next page here. Magnesium went from 23 up to 39, and so he realized that the other 16 must be oxygen. This concept really carries forward then, because when we start to write chemical equations, we have to write them in a balanced format. We can't have missing mass. Like, for example, let me write out an easy one here. Let's say I take some hydrogen and some oxygen, and I have it produce water. This looks so far like a reasonable statement. Sure, we have some hydrogens, we have some oxygens. Over here we have some hydrogens and oxygens. But if we start to count them, this hydrogen gas really involves two little H particles, right? This oxygen involves two little O particles. And then water, if we were to write it out, involves H, O, H. So if we start accounting for it, well, this one went here, and this one went here, and maybe this one went here. Hang on a sec. See the problem here? And so it seems so simple, but Lavoisier's discovery of law of conservation of mass was vital because now we could actually start realizing, hey, we have to balance our chemical equations. We need to actually put some numerical coefficients in front. We have to do something like this. You guys have all seen this before? Where we have to increase how many of them there are. So if we have two of these, one of these, and two of these, now all of a sudden, like this one balances that one, this one with that one. Now this one balances the remaining one. Now it's balanced, and from a subatomic particle perspective, not even a subatomic particle, but like from just an element perspective, all of the hydrogens that we started with, we still have later. All of the oxygens that we started with, we still have later. All of our protons are still there. All of our electrons are still there. Nothing can be gained, nothing can be lost. Does that make sense? So, long story short, that's a really long preamble for me trying to describe to you guys how we have to balance equations, right? Because if it breaks the law of conservation of mass, that is like one of the fundamental rules in chemistry. Kind of like in math, I teach almost all of you. I teach all of you math, actually. I teach all of you math. In math, like there's a couple of fundamental rules. One of them is like you can't divide by 0, right? Well, this would be a fundamental rule in chemistry. You have to balance equations. You have to start and end with the same amount of stuff. So that's my goal today. We want to work on chemical reactions. So, I mean, this is a really typical one right here. Just to make sure I'm being thorough, you guys know what we call stuff on this side over here? What do we call? Yeah, those are called reactants. This stuff over here on the other side of the arrow, products. Another word that you might hear me use once in a while is the word reagent. A reagent, I use that basically to describe like any chemical product or reactant. Okay? And the reason why I would use that is that imagine that you're in the lab, and a reagent that you might start with would be sodium chloride, but when you're done, you're going to have some sodium hydroxide, so you might still have some of this while you're making some of this. So if I ever use the word reagent, it really just describes anything that you might have at a given moment. You might have still some reactants because they're not all used up yet. You might have some products because you're starting to make it. So you get what I'm saying here? So if I ever use this word, it just really refers to any of these things here, just so that I have a catch-all word to describe them all. Okay, let's try an example. You guys should have done this at some point in your past. One thing you should be able to do then is start to write like a sentence involving a chemical reaction. You know, A plus B equals C. Right? So if I gave you words, solid magnesium metal reacts with aqueous hydrochloric acid to produce aqueous magnesium chloride and hydrogen gas, hopefully you'd be able to write it in like word format. So magnesium plus hydrochloric acid, arrow, magnesium chloride, hydrogen gas. You know, one of the cool things about Lavoisier is he realized that we needed to have a naming scheme. He actually helped develop the naming schemes we use of like the rules for like how to name stuff, because he realized that like this is kind of ridiculous to write this out in words all the time. Right? Normally we want to abbreviate it then and write it more like this. We need magnesium. We need hydrochloric acid. We need magnesium chloride. We need hydrogen gas. Isn't this a little bit more, isn't this faster? You know what I'm saying? Like this is a lot more concise. It's able to be a little bit more quick to be able to write it in this format. Now my goal today is to be able to help you guys do all of the pieces of the sentence we need. I kind of have a basic sentence here. You know, magnesium and hydrochloric acid makes magnesium chloride and hydrogen gas, but I'm missing so many things. Like if this was English and Miss Acion was marking this, she wouldn't be thrilled because you didn't capitalize the first letter, you didn't put a period at the end of your sentence, and maybe it's a sentence fragment or a run-on or something like. You know what I'm saying here? That's the analogy. because we should also do things like say, well, it was solid magnesium, and it was aqueous hydrochloric acid, and it was aqueous magnesium chloride, and it was hydrogen gas. That's one piece we should include. I say this a lot when I'm teaching kids at first. States of matter, matter. States of matter, matter. If this was, say, magnesium liquid, it probably doesn't react in the same way. The other thing, which is kind of the whole point I've been leading to, is that this breaks the law of conservation of mass. Right now I have one magnesium, and over here there's one magnesium. And then here I have one chlorine, and then here I have two chlorines. Well, all of a sudden I gained some chlorine. That doesn't make sense. And then conversely, here's one hydrogen, and now there's two hydrogens. Right? You guys get where I'm going here? We totally broke the law of conservation of mass, so we can fix that by putting a 2 there, if you've seen that before. And now we've written like a proper sentence. So, long story short, my goal today is to help you guys be able to write these sentences and do it properly, and hopefully this is review. Okay. If not, then just like I said to start class, make sure you ask me for lots of help. So, I'm just kind of breaking it up step by step. What did I do there to start? Well, the first thing I did is I created what's called the skeleton equation, where I just wrote out the bare bones basics, like say hydrogen plus oxygen makes water. I just wrote out the real basic elements, compounds even. Right. However, skeleton equations still aren't balanced because on the next step here we actually need to put coefficients in front. And again, I'm being super redundant, but this example right here isn't balanced, right? There's 2 hydrogen right here and 2 hydrogen right here. There's 2 oxygen right here. There's only 1 oxygen right here. Breaks the law of conservation of mass, so we need to put coefficients. Okay, so why don't we try some examples, because this should be a review. I think it's just best if I just do a couple and have you guys try some, and then we'll fill in the blanks after that. So here's the one I just talked about. How do I fix this one? You have 2 hydrogens here to 2 hydrogens here, 2 oxygen to 1 oxygen. So I'd say put a 2 here. That balances your oxygen. But as a byproduct, you now have 4 hydrogens. So if you put a 2 here, it solves it. You guys remember doing this? Yeah. Okay, I don't want to go too fast if this is not familiar. But like if I'm wasting your time, I want to speed up. So like here, you have 1 iron to 1 iron. That's fine. You have 2 chlorine to 3 chlorine. So put a 2 here, put a 3 here. Now you have 6 of each chlorine. And then put a 2 there for iron. Let me try one more, then I'll have you guys do the rest. This one's pretty complicated because there's a few different locations you have oxygens. So the advice I usually would give is if you have something that's like by itself in an elemental form, like this oxygen, do it last. It's usually the best advice. So like say there's 1 carbon, there's 6 carbons, so I'll put a 6 here. There's 2 hydrogens, there's 12 hydrogens, so I'll times this by 6 as well. And then you just need to be able to do math, right? So you got 12 oxygens here, plus 6 more gives you 18 oxygen on this side. Over here, this guy's got 6, which means I need this to add up to 12, but they come in packages of 2. So 12 in a package of 2 means you'd need 6. And then now you'd have 12 plus the 6 to also give 18 oxygens. Can you guys do this? Okay, why don't I give you a few minutes here just to try the last one here, and then there's also a few more on the next page. So why don't I give you like 5 minutes? Try them if you haven't already beat me to it. I'm sure some of you have gone ahead. And then I'll give you the answers. And then if this is something that you're like, oh my goodness, I don't know, then we can target it maybe like in a small group or one-on-one. Just to finish off the one on this slide here before I move it, hopefully you got 213, 810. Just call me over if you're stumped as to how I pulled that out. I'm just going to change the slide here so it can sit there for a second. Here, I'm just going to start throwing up some answers up there. Just check them as you go along. If you're not done, just don't look, right? What do you need to do? Put 2 there, 4 there, 2. Huh. Anybody notice the huge typo I have right about there? Anybody notice that? I wrote H3 gas. Probably should have been H2 gas. So, assuming that you changed it to H2 gas, because hydrogen doesn't actually come in threes, then you'd want that. That's a whoops. There. Is there a product missing on H or? Yeah, okay. Apparently my notes aren't very good. Okay, let's try to figure out what the other product would be. It would have to be an NH4. And then, let's see, the Ca goes to the PO4, NH4Br. This is a good time to talk about this, actually. If you're trying to figure out the state of matter, and you're not sure, where's a place that you can go to try to figure out what to put for state of matter? Go to your solubility table. All right, and then a quick look in the Br column. Is NH4 soluble with bromine? I'm pretty sure NH4 is soluble with almost everything. So just someone confirm that for me. Is NH4Br in that table aqueous? Okay. Right. So I know I said kind of earlier, if you're not sure, take a guess. Well, now using that table, you should be able to look it up and say, okay, this should be aqueous then. Okay. Sorry if you didn't get that far. Clearly, I have some errors on my notes still. That's weird. Disappeared. Okay, so we would need, what, 3 of those? No, that's going to screw things up, isn't it? We would need 3 of those. This one's a doozy. We're going to need 6 of those. We're going to need 2 of those. There we go. That does it. 6, 6, 6, 6, 3, 3, 2, 2. Yeah. That'll be a 4, and a 3, and a 4. Okay, here's some answers if you've gotten that far. Just check yours against mine. Let me know if you get something different, if one of us screwed up. Any issues? Okay. Do you guys feel like you have the general concept of how to balance? You may make a mistake here or there, right? But like, if you make a mistake, it's going to be because it's a facepalm rather than an over your head kind of mistake. Does that make sense? Okay. Well, this actually my mistake that I made right here by not having a product listed actually dovetails nicely with my next goal. Do you have the slide here? Let's not do this one. If you get the concept, let's move on. If you know you need more practice, though, here's a slide to do more practice. So, one of the things you might need to be able to do, though, is to predict what's going to be the products in a reaction. You know how there was that one missing where I screwed up? That actually wasn't intentional, but it sure led nicely into this bit here, which is if I give you the start of a sentence, you should be able to finish the second half of it, right, and kind of fill in the blanks. So if I give you A plus B, ideally you should be able to tell me, well, what is it going to turn into, and make predictions, right? Like, what would happen if you combined these or these or these together? And this actually is really purposeful because I could give you some stories in history of scientists who they didn't know really what they were doing, and they just were kind of messing around, and they just kind of, well, let's see what happens here and here. And when you don't know what's going to happen, sometimes the results are catastrophic. Anybody heard of Marie Curie? She discovered radium. They named an element actually after her, but one of the things about radium that Marie Curie didn't know at the time is that it's radioactive because it's radioactively decaying, and so it was giving off gamma rays, and she gave herself cancer and didn't realize that. She probably gave herself radiation poisoning actually. I'm not sure that she actually lasted long enough for cancer. I have to look that up. But she just didn't realize what she was working with at the time because it was just like, hey, this stuff is cool. Let's play with it, right? So, anyways, the point I want to make is that in modern chemistry, we don't want to just play because if you don't know what's going to happen, it could be horrible, right? Like, I'm not going to give you a couple of chemicals, say, here, just mix these, and all of a sudden a toxic gas comes up because as cool as that might sound, that's actually not fun in reality, right? So, long story short, we should be able to expect the products of a reaction. And there are 5 reactions so far that you hopefully have heard of. Over the course of the next year, when I teach you guys chemistry, you're going to learn at least 5 to 7 more kinds of reactions. But let me just list them off. And have you ever heard of formation, decomposition, single and double replacement, and combustion? Okay, those are 5. Over the next little while, I'm going to teach you guys about dissociation, ionization, reduction, oxidation, catalytic cracking, hydrogenation. Like we're going to add a huge list of chemical equations to what we already know. But hopefully these are 5 that we can kind of start with. Now, I just want to make sure that my point is made here. These 5, just so you know, that's not an all-encompassing list, right? Like the 5 that you've already learned, not every single chemical equation does not, in history, doesn't fit into this list. You know what I'm saying here? But it's a good start. So the first one you should know is formation, where you literally take 2 pieces like an A and a B, and you add them together and make an AB. You guys have seen this one before? Okay, I'm going to fast forward a bit here. Decomposition is the opposite. It's where you have a compound, an AB, and you break it up into its individual parts again. So literally 2 things coming together, and then they split apart. Real-world analogy, marriage and divorce. That makes sense? Union them, break them apart. Okay, single replacement can look a couple of different ways. I've actually written it out in letters right here. The best example I can think of an analogy would be like changing a partner in like dance, perhaps. You've got a dance couple that are dancing here, and then somebody else comes in, taps someone on the shoulder, and says, "Hey, can I have this dance?" And then they switch partners. It's the old switcheroo kind of concept. You ever heard that analogy before? That's what a single replacement is. It's a tap on the shoulder. Now it can happen two ways. Now I know, like, how do I say this nicely here? In chemistry, um, if the analogy makes sense here, in chemistry, guys always dance with girls. That makes sense. Positives have to dance with negatives. That's the only way that this works here. So that's why there's two ways of doing this here, because this could be a boy knocking out another boy, or a girl knocking out another girl. But like, you always have to have positives replace positives and negatives replace negatives. Okay? You can't have a single replacement reaction where when you're done, you're left with two cations. So double replacement then would, if you like the analogy, would be like a complete swap. It's where you've got A and B and C and D together, and this couple and this couple, they decide to just switch dance partners for the day. This one here, since I teach you all math, almost looks like a foil. It's almost like what you have to do is have A and D go together, and B and C go together. You see how that's kind of like when you're foiling something? It's not the entire part of it, but it's kind of like that. And then the last kind of reaction you should know about is combustion. And so far, you've probably just learned about hydrocarbon combustion. But while we're talking about this, really all combustion more or less looks the same way. You're going to have an initial product. You're going to add it to oxygen. It's going to form something, oxide, and another byproduct usually. So hydrocarbon combustion specifically usually involves carbon and hydrogen, and it makes CO2 and water. But that's actually not the only kind of combustion we could talk about. Like, for example, we could also combust, say, NH3. Well, the only change now is rather than producing a carbon dioxide, you might produce a nitrogen dioxide and water. Does that make sense? So I just want to point that out, is that it doesn't actually have to be carbons. You could change this carbon out for like some nitrogens or some sort of other. Usually it's got to be some sort of non-metal, like say sulfur. You can actually combust sulfur materials and make sulfur and oxygen. Let's write this out here. You could take sulfur and oxygen and make like a sulfur dioxide. In general, most combustions make a dioxide. In general, that's not like a hard and fast rule, but that's a common thing. It may not necessarily be carbon dioxide. It may be another type of dioxide. Okay. Like I said, the rules that you've learned so far for like the 5 reactions, they are not all encompassing, right? There are a million more types of reactions out there. But hopefully you'll kind of recognize that even something like this, I showed you this one to start class. This was the one that Lavoisier was working on. This is actually a combustion reaction in a way, right? What are you combusting? You're combusting magnesium, right? Now, I know it didn't make magnesium dioxide. The only reason why that happened here is that this is actually ionic, right? Because those guys are metals and non-metals. So it's a little bit different, but this is really combustion. So why don't we try some examples now? If I give you the stem to begin it, can we figure out what the end will be, so that we're not just flailing away in the lab going, hey, I wonder what happens? Because, like I said, as cool as that sounds, like in practice, that's super dangerous. Okay. So let's say I give you some lead for bromide. What kind of reaction is going to take place based on what you're seeing here so far? Probably decomposition, just because you literally are just starting with one item. So it's going to decompose into lead, and it's going to decompose into bromium. Okay, brief aside here. Have I talked with you guys about the word allotrope? Just to remember whether I have a slide on it somewhere or not. Do you guys know the word allotrope? Okay, an allotrope would be how bromine always comes in groups of 2. Hydrogen always comes in groups of 2. But sulfur sometimes comes in groups of 8. You guys ever heard of some of those things before? Yeah, like phosphorus comes in 4. I want to think there's one that does 3s. There's actually lots of different. By the way, the word for this then is called allotropes. Carbon, by the way, can do like carbon as a 1, carbon as a 4, carbon can be a 20, carbon can be, I think carbon can do a 2 actually. Okay, those are called allotropes. So it helps to know some of the common ones. The main ones I need you to know are all of the diatomics. Do you guys know all of the things that come in groups of 2? Hydrogen, and then if you got a periodic table, it's basically a little corridor around the outside. You've got nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. Can I snag this one on you? Just want to point it out to everybody. So if you need to know which ones naturally come in groups of 2, it's nitrogen, oxygen, fluorine, chlorine, bromine, iodide. All of these ones around the corner all come in groups of 2, as well as hydrogen. Okay, and it kind of sucks because you just need to know these ones. If you want to go to a Wikipedia article on it, you'll actually discover that some things have multiple different allotropes. I'm actually pretty sure that phosphorus can also do 3s, actually. But I need to go Google that. Because I think there's like a red phosphorus and a white phosphorus or something like that. So one of them is actually used in magic tricks because it spontaneously combusts after a while, which is really cool. Like it'll all of a sudden, just after a while, just light on fire on its own, which is like, you can see how that would be useful in a magic trick, right? Where you're doing your special thing, you walk over here, and then behind you, poof, it lights up. Anyways, I have to research when that is. I got off topic. Hopefully you guys get where I was going though here. This bromine right here has to come in groups of 2, because that's its natural allotrope for bromine. Okay, other punctuation we should include then. We need to know states of matter. Lead by itself, we should know its state of matter because lead's a metal. Almost all metals are solid, with few exceptions. Bromine, it's one of the very, very few that would probably be a liquid, right? Because it's blue on the periodic table. And then last step, this does not meet the law of conservation of mass because we're losing a couple of bromines, so throw a 2 here. There, we've now written ourselves an equation. Or at least we finished ourselves an equation. Does that make sense? Let's try another one. You've got nickel nitrate, nickel 3 nitrate it looks like, and then you've got a sodium sulfite. So first thing you'd have to ask yourself is what kind of reaction do I think is going to take place here? Yeah, double replacement, right? You've got a compound with a compound, so we got to switch them up. So we're going to want the nickel to go with the sulfate. We're going to want the sodium to go with the nitrate. I think I said that wrong. That's a sulfite and that's a nitrate. Next thing I got to do though is I got to make sure I write these compounds properly because I've kind of left a little gap here in case I need to throw a 2. So what is the charge on nickel? I think nickel can be either 2 or 3, but this particular nickel right here that we were working with looks like it was the 3 version. So then this nickel here is the 3 version. What's the charge on a sulfite? -2. Okay, so first I have to actually put the word together properly. Nickel with sulfite means you're going to want 2 of these for every 3 of those. That's the first bit. While I'm at it, why don't we grab a data table and figure out whether we think this thing should be solid or aqueous. So you're going to have to look up sulfite on the solubility table. Is sulfite on there? It is. So sulfite is like the third one from the right. It is not soluble with a lot of stuff though, only group 1 in ammonia. So this one right here, since sodium was in group 1, it would have been aqueous. But with the nickel, it would produce a precipitate and be solid. Everybody okay with that thought process I went through? First step was I need to know the charges to make the formula properly. After I made the formula properly, I still want to know what state of matter it's most likely going to be. And I did the same thing over here. This one's easier though. Sodium is a +1, nitrate's a -1, so they fit. So I don't even need any subscripts otherwise. I should look up whether it's solid or aqueous. I'm fairly certain that, and nitrate is like aqueous with like everything though. After a while, you'll like kind of know a few of them. nitrate is aqueous with group 1. Okay, last step. We should balance this guy because it actually isn't balanced in terms of the coefficients that go in front. One of the downsides is that let's say that you forgot to put this little 2 and this little 3 right here. You're totally going to screw up your balancing, aren't you? Right? So if you can't write the equation name, like the formula name properly, balancing is going to be a pain. Okay, where should I start? 2 nickels. I'm going to need 2 nickels here. It's going to give me 6 nitrates. So I want 6 nitrates there. And then I have 6 sodiums, so I'd want to put a 3 there. And if it works out, 3 sulfites is 3 sulfites. Hey, we're good. I know I went through that fast. Do you guys you're okay with being able to do that on your own, though? Let me just walk you through my thought process, though. Whenever I see a double replacement, I always actually do the same sort of steps. I do kind of like a big loop. I just pick one thing randomly to start with, and I go like from here to here, back to here, over to here, back to here. Like I basically go around in like a couple of circles, and eventually once I loop back on myself, once I get to the one thing that I didn't do, if it's balanced, we're good. So like I just randomly picked nickel first. There were 2 here, so I went over here and put a 2 there. Then I looked at what nickel was attached to, which was the nitrate, knew that I had 6, so I go to this side right here and I gave the nitrate 6. The nitrate is attached to a sodium, so I go back over here to this sodium and I need 3. And then the last thing should, if everything worked out, fit, because now 3 sulfites fits the 3 sulfites, and that's the last one that I didn't do. So if you ever get a double replacement, that process actually works really well. You just kind of go from here to here to there to there to there, and it should loop back on itself. That makes sense? Okay, let's try the next one. Zinc and sulfur. They're both in elemental form. I'm going to write them out here. Zinc is probably going to be by itself as a solid. I said this one a second ago. Sulfur actually comes often in, they actually call them flowers of sulfur. Sometimes actually that's what I buy them. Like when I go to my catalogs to buy chemicals, they call them flowers. And the reason why they call them flowers, I believe, is because they come in groups of 8. And the flowers are kind of like petals, I think is kind of the analogy, you know, like the petals on the outside of a flower there. So sulfur has a common allotrope of 8 in solids. And it kind of stinks because you have to just kind of have heard about what allotropes are common so that you're aware. And just whenever you hear of a new one, just write it down on your periodic table so that it's something where it's like, oh, sulfur comes in 8s. Okay, cool. Okay. These guys right here are going to probably combine in a formation reaction. Zinc is a 2+, sulfur is a -2, so we're good, right? We don't need any special coefficients. Or sorry, we don't need any special subscripts. Do you guys have sulfur in this version of your periodic table? Like on the solubility chart? Did they put sulfur on this one? No, they didn't put sulfur on this one. Shoot. Okay. You know how your periodic table doesn't have all the information in the world? Neither does your solubility table. We could go Google a solubility table that would tell us what sulfur is soluble with or not. But at this point here, I'm okay if you just pick solid or aqueous, okay? Like, if you should know, because it's in your data booklet, write it down properly, right? But if, like, you get what I'm saying here? This sulfur right here is not on your table, so we have no way of knowing without Googling it on your phone or something real quick. So, although this breaks every rule I have, why don't we just suggest that it might be aqueous? I don't care. If you pick solid, go solid, right? So, we could look this up if we had to. So, last step, we need 8 of each of these guys. There, now we've written our equation. Okay, let me do 2 more and then I'll let you guys kind of try some on your own. The next one here, I'm going to write down below. We need copper. We need gold 3 chlorate. Okay, you guys see you're going to be going back to your solubility tables a lot at times, right? So find chlorate and see whether gold is solid or aqueous in it. Chlorate, I believe, has a column, right? Yeah, it is. Chlorate's in the very, very first one there, chlorate. Now, there's only like 4 exceptions here, and gold chlorate's not one of them, so it looks like it's aqueous. Darian was right. Okay, what kind of reaction's taking place here? Single replacement, right? Because what's going to happen is this is a dance partner here, a boy and a girl, for example. Let's just, for the sake of argument, call gold the boy and chlorate the girl. And this boy over here, Copper, sees this really pretty girl over here and would like to ask her for a dance. And comes and taps this guy on the shoulder and says, "Can I have a dance, please?" And, do the whole switch. So we have to make sure we swap them out properly, though, right? So the copper will now go with the chlorate, and the gold, poor gold, it's all by himself now. Okay, now here's a problem, though. Copper chlorate. I have to know which version of copper chlorate it's going to form. How do I know which one it's going to form? Yeah, now, just so you guys are aware, it actually will form both. It'll form some some copper 1 chlorate. It would actually form some copper 2 chlorate. And so 2 reactions will probably happen simultaneously, and you get some of each. But for the sake of our course right here, if we're not sure which one to pick the first one listed. So copper lists the 2+ as being most common. So copper 2+ with a chlorate means you're going to need 2 of those guys. But just so you guys are aware, it's actually possible in chemistry for 2 reactants to combine and create products A and create products B at the exact same time. And it'll just randomly do some of each. You get what I'm saying there? But that's too much for where we're at right now. So let's just pick the most common one. Chlorate was aqueous with like everything, right? So that's an aqueous. And then gold by itself will be solid because it's black on your periodic table. Last step, we should balance. What do we need to balance? There's 2 of these to 3 of these, so I'll put a 3 here, a 2 here, which means a 2 and a 3 there. You guys have any questions on that? Okay, the last one's combustion. C6H14 is a liquid. Can I just pause for a second here on that thought? Why is C6H14 a liquid? Why does that make sense? It's like moderately big, right? Small small molecular compounds like CO2, CO, NO2, NO3 are usually gases. This one right here is kind of moderately big. If it was like C20H42, then it's probably like a solid. You guys actually probably know this to some degree. This right here is a component of gasoline. And you know how like we call it gas, but like when you put gas in your car, it's actually in liquid format, at least until we combust it, when we heat it up really hot. So anyways, that actually makes sense. This is a liquid. We're going to add it to oxygen gas. What are always the byproducts of a hydrocarbon combustion? CO2 and water. Okay, states of matter. What's the state of matter for carbon dioxide? Gas. State of matter for water. Gas, actually. I know liquid is most common. However, think about this for a second here, though. When you combust something, you're blowing it up, right? And you guys have all heard the words endo and exothermic at some point, right? It's going to be violently exothermic, thereby raising the temperature. I know that at room temperature, water is a liquid. But if you're going to blow something up, water is not going to be in liquid form because it would then immediately douse the fire. Say that again, right? Like when you blow something up in an explosion, I know it produces water, but it does not produce liquid water. It produces gas water because the temperature is going to be above 100 degrees Celsius. Does that make sense? So just make sure that you put hydrogen, water, gas as a vapor form, not liquid form. I know it seems silly, but I'm actually going to show. Actually, let's do it right now. This is not until later in the course, but I really want to develop these habits now. Can you guys find pages 4 and 5 in your data booklets? And Ryan, you'll just have to look at the one I'm stealing from you. Okay. This is a table which I'm going to show you how to use in the future. Obviously, we're not ready for it yet, but I want to show you why states of matter matter. Can you guys find water? They're the last, they're like in the bottom column there, there's two. There's one liquid water, there's one vapor water. Okay, now water still has the same chemical formula. It's still H2O, but can you guys see those numerical values, which obviously you don't know how to use yet? But do you see how those two numerical values are different based on the state of matter? This is why I'm trying to put it in your head right now. States of matter matter, okay? Because however those numbers work, clearly there is a difference between a water vapor and a water liquid. Okay, so if it feels like, Chris, you're being tedious, why do I have to know the state of matter? Hopefully I can kind of show you right there. This is why. Okay, last little bit then. All we have to do is balance. So what do we need? 6 carbons, 7. Shoot, this is one of those ones you have to double, isn't it? You guys are probably ahead of me, aren't you? 12, 14, 2. I'm blitzing through this. Do you guys know what I'm talking about, though? Like when you get one of these ones for combustion, where you have to like double the whole thing? Okay, if you maybe don't, because I want to stop. I want to give you some work time here. If you don't, call me over later, would you? What do we need then? 14 and 24 is 38? 19? Cool. Okay, let me stop because I'm getting the impression that since this is review, you guys are pretty comfortable with this. Okay, I think I have a little more on here where you guys can try it on your own, but why don't we call it a day? So, quick summary then. There are many different types of chemical equations, but I need you to know 5 basics for now, and then we're going to add more because that's the point of what we're doing. So you should know your combustion, your decomp, your formation, your single and double replacement. Later we'll learn ionization, hydrogenation, addition, substitution. Anyways, you guys don't need to know those yet. But you get where I'm going here. Like, not every single chemical equation fits into those 5 categories, but that should be a good start. Okay. I'm really picky, but it's for a reason. And I think I hopefully showed you some of those reasons. You have to balance them, because otherwise it breaks laws of conservation of mass. You have to include states of matter, because states of matter actually matter, believe it or not. Okay. So if you can do all those details, now you can start writing sentences. And then the only thing we have left to do is tomorrow, I think it was, tomorrow we're going to talk about a mole, which is like molar masses. And now we start adding some numbers where we use grams and moles, and we figure out how much something weighs. So just one quick thought. If you guys don't have a calculator, can you try to bring one tomorrow? Because you're going to want it going forward. So, okay, I've talked for way too long. You guys have like almost half an hour. Work on whatever it is you need, or call me over, or, I don't know, do whatever, I guess. Sound good? Okay, and break.